3I Atlas is gone. After a breathtaking journey through the inner reaches of our solar system, this enigmatic interstellar wanderer is now retreating back into the cosmic darkness from which it emerged. But here's what makes this moment so significant. All of our most advanced telescopes, our most sophisticated scanning equipment, every instrument we could possibly aim at the heavens managed to capture one final, comprehensive look at this mysterious object as it departed our neighborhood. What does that mean for us? It means we now possess more detailed information about 3I Atlas than we've ever gathered about any other interstellar visitor that's crossed our path. And with that wealth of data comes something we've been desperately seeking: the ability to finally draw some meaningful conclusions about what this enigmatic object actually is. Or perhaps more importantly, what it isn't. In December 2025, our planet experienced its closest approach to 3I Atlas, offering humanity an unprecedented view of the object for the first time in many months. Throughout most of October and November, 3I Atlas had essentially vanished from our view, concealed behind the brilliant glare of our sun. During those hidden weeks, something profound was happening. The intense heat and relentless radiation pouring from our star had been transforming 3I Atlas in ways that would fundamentally alter everything we thought we knew about it. Scientists anticipated seeing a drastically different object when it finally emerged from behind the sun. And that expectation? It turned out to be absolutely correct. When the Hubble Space Telescope captured its images of 3I Atlas, what appeared was almost surreal. There, suspended in the darkness, was a minuscule bright point of light. But that tiny dot was surrounded by an absolutely massive haze of gas and dust. This shroud, which astronomers call a coma, is actually quite typical when you're looking at a comet. Under normal circumstances, we'd also expect to see an elongated tail streaming away from that coma, stretching across the void like a cosmic banner. But 3I Atlas has proven itself to be anything but normal. To truly understand what 3I Atlas was doing, scientists needed to examine these images in an entirely different light. When researchers processed the Hubble imagery through what's known as a rotational gradient filter, something remarkable became visible. This technique essentially strips away anything circular from the photograph, leaving behind only the distinctive jets of gas that were erupting from the surface of 3I Atlas. And if you're thinking that sounds unusual, you'd be absolutely right to think so. On the left side of these processed images, the tail of 3I Atlas finally revealed itself. The overall shape matched what you'd typically expect from a comet. But there was one glaring problem with what we were seeing. The direction was completely wrong. This tail wasn't streaming away from the sun like it should have been. Instead, it was pointing directly toward our star. For almost the entire duration of our observations of 3I Atlas, this object had been displaying clear evidence of what astronomers call a sun-facing tail, or more technically, an anti-tail. Now, you might be wondering why this is such a big deal. Here's why. In every single other comet that humanity has ever observed, without exception, the tail always streams away from the sun. This happens because of something called the solar wind, which tends to push back all of the dust and gas that makes up the coma. Don't let the term wind confuse you, though. There's no actual wind in space, at least not in the way we experience it on Earth. What we're really talking about is a constant, unrelenting stream of charged particles and radiation that continuously pours out from the surface of our sun. This stream carries enough energy with it to produce the same effect as atmospheric wind would, but on any matter in the solar system that isn't anchored down by a powerful gravitational field. Given everything we know about how comets behave, scientists naturally expected that as 3I Atlas drew nearer to the sun, the anti-tail would gradually shrink as the object experienced increasing pressure from the solar wind. That's what should have happened. That's what all our models predicted. But once again, 3I Atlas defied our expectations entirely. What we were actually witnessing was something far more intriguing. There was an enormous jet of gas and dust erupting from the sun-facing side of the object, and it was substantial. This meant that deep within 3I Atlas, there had to be an incredibly large amount of energy forcing this material outward, essentially overpowering the energy radiating from our sun itself. Think about that for a moment. This relatively small object was generating enough internal pressure to counteract the solar wind, something that requires tremendous force. But if you think that's the strangest part of what we observed, wait until you hear about what appeared on the opposite side of 3I Atlas. To the right of the object in the processed images, there was something that might be even more perplexing than the antitail. A trio of jets, 3 distinct streams of material shooting out into space. The largest of these jets occupied the position where a typical comet tail should logically appear. But flanking it on either side were 2 additional, smaller tails, and together, the 3 of them created an almost geometrically perfect triangular pattern. It's precisely this kind of observation that fuels speculation about whether we might be looking at something of artificial origin, something created by intelligence. And admittedly, it is pretty weird. The symmetry, the precision, the unexpected behavior, all of it seems to suggest something beyond natural processes. But before we jump to any dramatic conclusions, we need to exercise scientific caution. Drawing definitive interpretations from a single observation, no matter how striking, would be premature and potentially misleading. These massive jets of gas and dust erupting from 3I Atlas do provide us with something incredibly valuable, though. They offer a window into the composition and internal structure of the object. And that information is going to reveal a tremendous amount about what this thing truly is, where it came from, and why it behaves so differently from anything else we've encountered. When scientists first began observing this interstellar visitor back in the summer of 2025, it was already producing a coma filled with some genuinely bizarre substances. The primary component? Carbon dioxide. And that's not at all what you'd expect to see pouring from a comet, or at least not from any comet that originated in our solar system. You see, all of the comets that orbit within our solar system share a common composition. They're almost entirely constructed from water ice. Sure, they do contain some frozen carbon dioxide mixed in, but the proportion is quite small when compared to their water content. Water dominates. It's the primary ingredient by a massive margin. 3. I-Atlas completely inverted that expectation. It was outgassing enormous quantities of carbon dioxide while producing only minimal amounts of water vapor. At least, that's what appeared to be happening until the object encountered the sun's influence directly. Then everything changed in spectacular fashion. Using sophisticated radio-based instruments, such as the Meerkat telescope array located in South Africa, astronomers developed the capability to penetrate through the dense coma of gas and dust that surrounded 3I Atlas. These instruments allowed them to begin analyzing the actual composition of those jets that were shooting out from the object's surface. And this is where researchers made a discovery that would fundamentally reshape our understanding of what 3I Atlas really is. They found water, not just traces of it. Lots and lots of water. Suddenly, the picture became much clearer. Beneath the surface of 3I Atlas, hidden from our initial observations, the object was absolutely loaded with water ice. And once the sun's heat had warmed the object sufficiently, that water began erupting outward at truly staggering rates. This discovery actually provides us with an enormous clue about how the object might have originally formed and what factors contribute to its bizarre behavior. So here's the leading theory that's currently gaining traction among researchers. And it's fascinating. We know several things about 3I Atlas, with reasonable certainty. We know it's ancient. Not just old, but genuinely ancient. Older than our planet Earth. Older than our sun. It originated somewhere far across our galaxy, in a region of space separated from us by unfathomable distances. This object has spent an incomprehensible amount of time drifting through the vast emptiness that exists between star systems. And during all of that time, during those billions of years of wandering, it's highly probable that 3I Atlas never approached a star as closely as it just did when it passed through our solar system. Now, we can't track 3I Atlas's trajectory backward with perfect precision all the way to its point of origin. The distances and timescales involved are simply too vast. What we can determine is that it approached us from the general direction of the galactic core, that dense region at the center of our Milky Way galaxy. But here's what's truly remarkable. Based on our calculations, for at least the past 10 million years, this object hasn't come within 1 light-year of any star whatsoever. That's an incredibly long time of complete stellar isolation. In theory, this means there's been absolutely nothing capable of disturbing the object from whatever state it existed in when it was first ejected from its home system. No stellar wind to erode it, no heat to melt its surface, no gravitational perturbations to alter its composition, just endless darkness and cold and silence. Except here's the thing. Space isn't entirely empty. Even in the regions between stars, where matter is spread so thin that we often describe it as a vacuum, there exists an invisible but powerful force that pervades the galaxy: galactic cosmic rays. These aren't rays in the traditional sense. They're essentially the remnants of dying stars, the aftermath of massive supernovae that exploded with such violence that they blasted powerful radiation outward through interstellar space in all directions. This radiation propagates across the galaxy, penetrating even the darkest voids. And 3I Atlas has been soaking in this cosmic radiation for billions upon billions of years. Those cosmic rays would have been constantly bombarding the surface of the object, attacking it at the molecular level. They would break down chemical bonds, rearranging atoms, and converting molecules. Water ice and simple carbon compounds would gradually transform into carbon dioxide. Over millions and millions of years, this process would create something quite unusual: a thick radiation crust covering the entire exterior of the object, fundamentally altering its appearance and composition from whatever it originally was. Following this theoretical framework, 3I Atlas could very well have begun its existence as a completely typical water ice comet, formed in a solar system not unlike our own. Perhaps it orbited a star similar to our Sun, accumulating ice and rock in the outer regions of that distant planetary system. Then one day, billions of years ago, it made a fateful close pass by a massive gas giant planet. The gravitational interaction would have been violent, flinging 3I Atlas away from its home star at tremendous velocity, launching it on a trajectory that would send it careening out into the depths of interstellar space. There, alone in the darkness, it would have slowly, gradually, developed this mutated exterior shell, shaped and transformed by the relentless bombardment of cosmic radiation over incomprehensible timescales. The pristine water ice comet that began this journey would have been completely encased in a shell of radiation-altered material unlike anything that exists in our own solar system. And then, after billions of years of solitude, after drifting through the galaxy for longer than complex life has existed on Earth, it finally began approaching another star, our Sun. As 3I Atlas drew closer to our solar system, the Sun's heat started working on that radiation crust, breaking it down, causing it to sublimate and release all of this strange cosmic material that had accumulated over the eons. The gases and compounds that poured out initially were so unexpected, so different from normal comet composition, that they completely baffled every scientist who observed them. But as 3I Atlas continued its approach, as it grew hotter and hotter from solar radiation, something more dramatic began to happen. The crust started to fracture. It began breaking apart, and that long-dormant icy interior, the pristine water ice that had been sealed away for billions of years, suddenly burst forth in spectacular fashion. The water couldn't flow uniformly across the surface, though. It could only escape through the cracks and holes in that thick radiation shell, creating concentrated jets that blasted outward in seemingly random directions. So in simple terms, this theory suggests something profound. 3. Atlas isn't actually a weird comet at all. It's a perfectly normal comet that happens to be trapped inside a highly unusual shell of cosmic material that we've never encountered before. That shell is what made everyone react with such surprise and confusion. That shell is what caused all the speculation and debate. And if you're still not convinced that this isn't evidence of alien technology, consider this. Here are the people whose entire professional existence is dedicated to finding aliens, and they're saying definitively that it's not aliens. The SETI Institute is a nonprofit research organization that was founded back in 1984 with a very specific mission: exploring the origins of life throughout the universe and conducting the search for extraterrestrial intelligence. These are the experts, the professionals who have devoted their careers to this question, and they spent the last month utilizing an incredibly wide variety of instruments and telescopes from locations all over the world to observe 3I Atlas in every conceivable way. They examined it through infrared light, ultraviolet light, radio waves, microwaves. They were desperately searching for any indication of what they would classify as a techno-signature, which is essentially any sign that would indicate the presence of intelligent technology. And what did they find? I'm sorry to say, they didn't find anything. Nothing. Not a single indication of artificial origin. The sophisticated methods they employed to scan 3I Atlas would have been sensitive enough to detect any kind of transmitter or communication device up to 10 times weaker than an ordinary cell phone. So, if this object was actually an alien probe attempting to communicate with some distant civilization, calling home across the light years, we absolutely would have detected those transmissions. We did not. At least, that's the official statement from the people in positions of authority. But here's where things get interesting, because not everyone is entirely satisfied with that explanation. There's an organization called the Black Vault. It operates as an online archive dedicated to collecting and publishing declassified government documents, particularly those obtained through Freedom of Information Act requests. They decided to submit a formal FOIA request to the Central Intelligence Agency, asking for the release of any communications, documents, or records involving 3I Atlas. What they received in response was peculiar. Instead of simply stating, "No, we don't possess any documents related to that topic," which would be the standard response if they truly had nothing, the CIA provided a much more cryptic answer. They told the Black Vault, "We can neither confirm nor deny the existence or non-existence of such records." Now, that's a very specific type of response. It's the kind of carefully worded statement that government agencies typically deploy as a legal defense mechanism, a way of protecting themselves so they can later claim they never actually lied about anything. But the CIA's response went even further than that. They also stated, "The fact of the existence or non-existence of such records is itself currently and properly classified." Think about what that implies. If 3I Atlas is genuinely just a large chunk of ancient ice drifting through space, if it's simply a natural object with no connection to intelligence of any kind, then what possible information about it would require classification by the United States government? What could be so sensitive that even acknowledging whether or not they have any information about it could compromise national security? The truth is, I don't know the answer to that question, and I don't imagine we'll ever receive a straight answer, at least not in our lifetimes. The machinery of government secrecy doesn't easily yield its mysteries, especially when it comes to topics that touch on national security, aerospace capabilities, or anything that might fall under the broad umbrella of classified intelligence operations. But here's what I can tell you with absolute certainty. 3. I-Atlas will not be the last interstellar object that generates this kind of debate. It won't be the last time we have these conversations about whether something from beyond our solar system might represent evidence of extraterrestrial intelligence. With new observation technology coming online, particularly instruments like the Vera Rubin Observatory, which possesses the capability to record a high-resolution image of the entire visible night sky in just a couple of days, we're standing on the threshold of a completely new era in astronomy. An era where the hidden secrets of our solar system and the space beyond it will finally be revealed in unprecedented detail. Consider this. In the past 10 years, we've managed to detect and identify exactly 3 interstellar objects passing through our solar system. 3. That's it. But that number tells us something crucial. It tells us these objects aren't particularly rare or uncommon. They're probably passing through our neighborhood fairly regularly. We've simply been terrible at spotting them. Our detection capabilities have been too limited, our survey coverage too sparse. But that's changing rapidly. As our observational technology improves, as our sky surveys become more comprehensive and more frequent, we're going to start detecting these interstellar visitors at an accelerating rate. And that's going to open up an entirely new realm of scientific investigation. By studying many of these objects, by gathering data on dozens or hundreds of interstellar visitors, instead of just a handful, we'll finally be able to establish baselines. We'll be able to determine what constitutes normal behavior and composition for objects originating from other star systems. And perhaps most exciting of all, we'll develop the expertise to recognize what's actually anomalous, what genuinely defies explanation. Because here's the thing, the really weird stuff, the objects that might actually challenge our understanding of what's possible, they're still out there, Somewhere, in the vast darkness between the stars, objects far stranger than 3i Atlas are waiting to be discovered. Objects that might force us to reconsider everything we think we know about the universe we inhabit. The story of 3i Atlas doesn't end with its departure from our solar system. In many ways, the real story is only just beginning, because the data we've collected, the observations we've made, and the questions we've raised will continue to reshape our understanding of interstellar space for decades to come. Let's talk about what we've actually learned from this encounter, and why it matters so much for the future of astronomy and our search for life beyond Earth. One of the most significant revelations from our study of 3i Atlas relates to the sheer diversity of objects that exist in interstellar space. Before we started detecting these wandering visitors, our understanding of what existed between the stars was largely theoretical. We had models and simulations, educated guesses based on what we observed in our own solar system, and in distant star-forming regions. But direct observation? That was essentially impossible until very recently. 3i Atlas has taught us that the space between stars is far more populated and far more dynamic than we previously imagined. It's not just empty void punctuated by the occasional rogue planet or escaped comet. It's a complex environment filled with objects of varying sizes, compositions, and origins, each one carrying with it a unique history that spans billions of years. Think about what that means. Every interstellar object that passes through our solar system is essentially a messenger from another part of the galaxy. It's a sample of materials that formed around a different star, under different conditions, perhaps billions of years before our own sun ignited. These objects are cosmic time capsules, preserving information about stellar systems that may no longer even exist. When we examine the composition of 3i Atlas, when we analyze the ratios of different chemical compounds in its jets and coma, we're not just studying one object. We're gathering clues about the processes that occurred in another solar system, potentially hundreds or even thousands of light years away. We're learning about the conditions that existed there, the types of materials that were available, the ways in which planets and smaller bodies formed and evolved. The radiation crust that we believe encases 3i Atlas presents another fascinating avenue of research. If our theory is correct, if cosmic rays truly can alter the surface composition of objects drifting through interstellar space over millions of years, then we need to completely rethink how we interpret observations of these visitors. Consider the implications. When the next interstellar object appears in our telescopes, when we start analyzing its composition and behavior, we can't simply assume that what we're seeing on the surface reflects what lies beneath. We need to account for potentially billions of years of radiation exposure, of chemical transformation, of gradual metamorphosis, driven by the harsh environment of deep space. This has profound consequences for how we classify and categorize these objects. Is something a comet because it has a coma and a tail? Or is it a comet because it's fundamentally composed of ices and volatiles, regardless of what kind of shell might have formed around it? These might seem like academic distinctions, but they're actually crucial for building accurate models of how planetary systems evolve and how material moves through the galaxy. The unusual jets we observed on 3i Atlas also tell us something important about the internal structure of these objects. The fact that water could only escape through specific cracks and fissures in the radiation crust suggests that the interior remained relatively pristine, even as the exterior was being transformed. That's actually quite remarkable when you think about it. It means that deep inside 3i Atlas, protected by that altered outer layer, there might still exist water ice that formed billions of years ago around another star. Water molecules that condensed in the outer reaches of an alien solar system that were never touched by stellar heat or radiation until they finally encountered our sun. Those molecules carry information encoded in their isotopic ratios, in the trace elements they contain, in their crystalline structure. If we could somehow retrieve a sample from the interior of an object like 3i Atlas, if we could bring that pristine material back to Earth for detailed laboratory analysis, it would revolutionize our understanding of how solar systems form. We could directly compare the building blocks of another planetary system to the materials that formed our own planets. We could test theories about the distribution of elements throughout the galaxy. We could search for organic molecules that might provide clues about the potential for life elsewhere in the universe. Of course, retrieving such a sample presents enormous technical challenges. These objects are moving at tremendous velocities relative to our solar system. 3. I-Atlas was traveling at approximately 25 kilometers per second when it passed through our neighborhood. That's fast. Really fast. Catching up to something moving that quickly, matching its velocity, and then somehow extracting a sample and returning it to Earth would require propulsion systems and mission architectures far beyond our current capabilities. But that doesn't mean it's impossible. Just extremely difficult with present technology. Several space agencies and research organizations have already begun preliminary studies on potential missions to intercept future interstellar objects. The basic concept involves having a spacecraft ready to launch at very short notice, positioned in a high Earth orbit where it can quickly depart for deep space. When sensors detect an incoming interstellar visitor, the spacecraft would launch immediately, using a trajectory calculated to intercept the object somewhere in the outer solar system. The spacecraft wouldn't need to match the object's velocity completely. It could perform a high-speed flyby, using advanced instruments to gather as much data as possible in the brief moments when it's close to the target. Or, with sufficient propulsion capability, it might deploy a small impactor that would strike the object and create a debris plume, allowing the main spacecraft to fly through that plume and collect samples. These mission concepts are still in the very early stages of development, but the encounter with 3I-Atlas has added urgency to the planning. We now know that these objects visit our solar system with some regularity. We know they carry scientifically invaluable information, and we know that our ground-based telescopes, as powerful as they are, can only tell us so much. To truly unlock the secrets these visitors carry, we need to go out and meet them. The question of whether 3I-Atlas could be artificial, whether it might represent some kind of alien technology, deserves more careful consideration than simply dismissing it out of hand. Not because there's compelling evidence that it is artificial there isn't, but because asking that question seriously forces us to think about what kinds of signals or signatures we should actually be looking for. The SETI Institute's search for technosignatures focused primarily on electromagnetic emissions, radio signals, microwave transmissions, the kinds of communication technologies that we humans use. And that makes sense as a starting point. If an alien civilization wanted to send a probe that could call home across interstellar distances, equipping it with a radio transmitter would be a logical choice. Radio waves travel at the speed of light and can carry complex information across vast distances with relatively little degradation. But what if we're thinking about this wrong? What if an advanced civilization wouldn't use electromagnetic signals at all, at least not in the way we expect? Consider for a moment the possibility that a truly advanced technological civilization might develop communication methods that we literally cannot detect with our current instruments because we don't even know they're possible. Technologies based on physical principles we haven't discovered yet. Or perhaps they would use quantum entanglement for instantaneous communication, eliminating the need for any signal that propagates through space at all. Or, here's another thought. What if an interstellar probe wouldn't actively transmit anything? What if it was designed to be completely passive, simply observing and recording, storing information internally to be retrieved at some future time? Such a probe could pass through our solar system entirely unnoticed, gathering data about our planet, our civilization, our technological development, without ever announcing its presence. We tend to assume that any alien technology would want to communicate, would want to be found. But that assumption is based entirely on human psychology and human motivations. We have no idea what drives the decision-making of a hypothetical alien intelligence. They might have perfectly valid reasons for wanting their probes to remain undetected. None of this is to suggest that 3I-Atlas actually is such a probe. The evidence overwhelmingly supports the conclusion that it's a natural object, a comet with unusual properties, but fundamentally still just a comet. But the exercise of seriously considering the alternative helps us refine our search strategies and expand our thinking about what we might eventually discover. The classified response from the CIA regarding 3I-Atlas documents raises questions that extend beyond this single object. It touches on a broader issue about how governments handle information related to potential extraterrestrial phenomena, and whether the public has a right to know what, if anything, official agencies might have discovered Over the past several years, there's been a notable shift in how the United States government discusses unidentified aerial phenomena, or UAPs. What was once a topic relegated to the fringes of conspiracy theories has been legitimized through official Pentagon reports, congressional hearings, and the establishment of dedicated investigation offices. Military pilots have come forward with accounts of encountering objects that displayed flight characteristics beyond known human technology. Videos have been declassified and released to the public, but the nature of government secrecy means we'll likely never know the full story behind what any intelligence agency might know about interstellar objects or other unusual phenomena. There are legitimate reasons for classification that have nothing to do with hiding evidence of aliens. A government might classify information about how they track and observe objects in space because revealing those capabilities could compromise national security. If an adversary knows exactly what you can and cannot detect, they know how to avoid your detection systems. The CIA's response to the Black Vault could simply reflect standard operational security protocols. By refusing to confirm or deny the existence of documents, they maintain maximum flexibility. They don't reveal their intelligence gathering capabilities, they don't set precedents for future FOIA responses, and they don't accidentally confirm or deny anything that might be sensitive for reasons unrelated to the nature of the object itself. Still, the response feels unsatisfying, doesn't it? When something as unusual as 3I Atlas passes through our solar system, when scientists around the world are analyzing it and debating its nature, the idea that government agencies might possess additional information that we're not allowed to see creates a sense of frustration. We want to know everything there is to know. We want complete transparency. But we also live in a world where nation-states compete for strategic advantage, where information is power, and where some things genuinely do need to remain secret for legitimate security reasons. Finding the right balance between public transparency and necessary secrecy is an ongoing challenge that won't be resolved anytime soon. What we can do, as members of the public interested in these questions, is support open scientific research and independent investigation. The more civilian astronomers can observe and analyze these objects using instruments not controlled by any government, the less we have to rely on official sources for information. The SETI Institute, for example, is a private nonprofit organization. Their findings are published openly and subjected to peer review. That's the kind of research infrastructure that helps ensure transparency. Looking toward the future, the technological improvements coming online over the next decade will dramatically transform our ability to study interstellar objects. The Vera Rubin Observatory, which I mentioned earlier, represents just one example of the new generation of instruments that will revolutionize astronomy. This observatory, located in Chile, features an 8.4-meter primary mirror and a camera containing 3.2 billion pixels. That makes it the largest digital camera ever constructed for astronomy. But the truly revolutionary aspect isn't just the size of the camera, it's how the observatory will be used. Unlike traditional telescopes that focus on small patches of the sky for extended periods, studying individual objects in great detail, the Vera Rubin Observatory will conduct what's called the Legacy Survey of Space and Time. It will systematically photograph the entire visible sky, over and over again every few nights. Each image will be immediately compared to previous images of the same region, allowing astronomers to detect anything that has changed or moved. This approach will be devastatingly effective at finding interstellar objects. These visitors move against the background stars, creating a distinctive pattern across sequential images. The survey will spot them automatically, triggering alerts that will allow astronomers around the world to immediately point other telescopes at the newly discovered object for detailed follow-up observations. Current estimates suggest the Vera Rubin Observatory might detect several interstellar objects per year once it's fully operational. Some years might see dozens of discoveries. Instead of studying 3 interstellar visitors over the course of a decade, we might accumulate data on hundreds of them over the same time span. That's the kind of statistical sample size that allows for real scientific analysis. With that many objects to study, patterns will begin to emerge. We'll learn what's common and what's rare. We'll understand the typical compositions, the usual trajectories, the standard behaviors. And when something genuinely anomalous appears, something that doesn't fit the patterns we've established, we'll recognize it immediately. That's when things will get really interesting. Other technological developments will complement these observational improvements. Spectroscopic instruments are becoming more sensitive and more sophisticated, allowing us to analyze the chemical composition of distant objects with increasing precision. Interferometric techniques let us combine data from multiple telescopes to achieve resolution equivalent to an instrument the size of the Earth itself. Space-based telescopes eliminate the distorting effects of our atmosphere, providing crystal clear images of even faint objects. And perhaps most importantly, advances in computational power and machine learning algorithms are making it possible to process enormous quantities of astronomical data far more efficiently than ever before. The Vera Rubin Observatory will generate approximately 20 terabytes of data every single night. No human could possibly examine all of that manually. But sophisticated software can scan through it automatically, flagging anything interesting for human review. These technologies working together will create an unprecedented surveillance network for our solar system. Nothing significant will be able to pass through without us knowing about it. Every asteroid, every comet, every interstellar visitor will be cataloged and tracked. Their orbits will be calculated, their compositions analyzed, their potential hazards assessed. This comprehensive monitoring serves multiple purposes beyond pure scientific curiosity. It's also about planetary defense. The same systems that detect interesting interstellar visitors can also identify potentially hazardous asteroids that might pose a collision threat to Earth. The earlier we spot such objects, the more options we have for dealing with them. But let's return to 3I Atlas one final time, because there's a deeper philosophical point worth making about what this object represents. When 3I Atlas entered our solar system, it had already been traveling through space for an inconceivable length of time. It might have been ejected from its home system before multicellular life existed on Earth. It wandered alone through the darkness, through regions of space so empty that the nearest star was light years away in any direction, for longer than our entire civilization has existed. And then, by cosmic chance, its trajectory brought it here, to our solar system, to this tiny corner of the galaxy, where one particular species of intelligent ape had recently developed telescopes and the curiosity to point them at the sky. We had just a few months to observe 3I Atlas, a fleeting moment in cosmic terms, and then it was gone, continuing on its eternal journey to destinations we can't even imagine, toward corners of the galaxy it won't reach for millions or billions of years. But in that brief moment of intersection, that chance encounter between this ancient wanderer and our newly technological civilization, we learned something. We expanded our understanding of the universe. We gathered data that will inform research for generations. We asked questions we'd never thought to ask before. That's what makes these encounters so precious. They're rare. They're unexpected. They're opportunities to glimpse something beyond our everyday experience, to touch something that connects us to the broader cosmos in which we exist. 3. Atlas reminded us that our solar system isn't isolated. It's part of a galaxy, teeming with other solar systems, other stars, other worlds. Material flows between these systems constantly, carrying with it information and elements, and perhaps, someday, life itself. We exist in a dynamic, interconnected cosmic ecosystem far more complex than we typically consider in our daily lives. Every interstellar object that visits us is a gift. It's a chance to learn about places we may never physically reach, to understand processes occurring across vast distances, to test our theories about how the universe works. The fact that we can now detect these objects, study them, analyze their composition and behavior, represents a remarkable achievement of human ingenuity and persistence. Less than a century ago, we didn't even know galaxies existed beyond our own Milky Way. We thought the universe was static and eternal. We had no concept of the Big Bang, no understanding of stellar evolution, no knowledge of planets beyond our solar system. The progress we've made is staggering, and it continues to accelerate. As we look toward the future, as we prepare for the discoveries that await us, it's worth remembering that 3I Atlas is just the beginning. It's one of the first interstellar visitors we've been able to study in detail, but it certainly won't be the last. With each new object we detect, with each new dataset we analyze, our understanding deepens. The picture becomes clearer. We're learning to read the cosmic messages that have been flowing through our solar system all along, messages we simply lack the tools to perceive. We're decoding the history of our galaxy one interstellar visitor at a time, piecing together a narrative that spans billions of years and light years of distance. And somewhere out there, right now, another interstellar object is heading our way. It might arrive next year, it might arrive in 10 years, but it's coming. And when it does, we'll be ready. Our telescopes will track it. Our instruments will analyze it. Our scientists will study it. And we'll ask once again, what are you? Where did you come from? What can you teach us about the universe? The cosmos is full of wonders waiting to be discovered. Objects stranger than we can imagine. Phenomena we haven't yet dreamed of. Secrets that will challenge everything we think we know. 3i Atlas gave us a taste of that mystery. That sense of encountering something from beyond our familiar neighborhood. The next visitor might be even more extraordinary. It might force us to rewrite textbooks and revise theories. It might present us with observations so anomalous, so difficult to explain through conventional physics, that we have no choice but to consider possibilities we've previously dismissed. Or it might be mundane. Another chunk of ice and rock, following a trajectory determined by gravity and chance, carrying nothing more remarkable than frozen water and cosmic dust. Either way, we'll learn. We'll grow. We'll continue the grand project of understanding the universe we inhabit. That's the real legacy of 3i Atlas. Not any particular scientific finding, though those are valuable. Not the speculation about aliens or the cryptic government responses, though those are intriguing. The real legacy is simpler and more profound. It reminded us to look up, to pay attention, to remain curious about what lies beyond our world. In an age where we're often focused on immediate concerns, on the challenges and crises of our daily existence, these cosmic visitors offer perspective. They remind us that we're part of something vast and ancient, that our planet is just one small world in an incomprehensibly large universe, and that there are mysteries out there worth pursuing, even if they don't offer immediate practical benefits. Science isn't just about solving problems or developing technologies, though it does those things. It's also about satisfying curiosity, about expanding the boundaries of human knowledge, about reaching toward understanding simply for the sake of understanding. 3i Atlas is gone, but it leaves behind something valuable. Questions to answer, data to analyze, and the certainty that more wonders await discovery. The universe is speaking to us, sending messengers across the void. We're finally learning to listen.